Hi everybody. So in today's lecture, I'd like to talk to you about macrostates, microstates, multiplicity, and combinatorics. And this is for Chapter 2 in thermodynamics. We're starting in Schroeder's textbook, Thermal Physics, and we're going to get started with that. So first of all, let me define the terms microstates and macrostates. A microstate is a particular configuration of the individual constituents of the system, whereas a macrostate is a description of the conditions from a macroscopic point of view. So you might use, for example, state variables like pressure, density, temperature to describe the macrostate of a system. I have 1 atmosphere of pressure for an ideal gas in a volume of 1 cubic meter at a temperature of 273 Kelvin, right? And that's the description of the system from a macroscopic point of view. A microscopic description of that system would mean that you describe how fast, in what direction, and at what location each one of those gas molecules is. See, so that's very different, okay? So let's talk about macrostates and how we describe them in thermodynamics. So for a given macrostate, a number of microstates are possible. For that ideal gas example, there would be tons of microstates that would describe 1 atmosphere of pressure at 273 Kelvin and 1 meter cubed of an ideal gas. There would be tons of ways that could be arranged. Now, the number of ways that that can be described, the number of microstates associated with a given macrostate of the system, is called the multiplicity. And we often use the Greek letter omega, the capital Greek letter omega, to describe that. Now, in thermodynamics, there's a very important assumption that we make, and that's that all microstates for a given macrostate are equally probable, okay? That's a very important assumption, and you should memorize that. When all possible macrostates of a given system are examined, we find that the macrostates associated with disorder have more microstates than those associated with order. In other words, if you have a completely disordered system, it's going to have a lot of microstates associated with it, whereas a very ordered system has just a few microstates associated with it. Now, this all might seem pretty abstract, okay? So what I'd like to do is use a really concrete, easy to understand example to describe this. And my favorite one is poker, okay? So if you're not familiar with it, poker is a card game that people oftentimes bet on. I'm really bad at it, by the way, because I have no poker face, but that's completely different, completely separate issue. Let's talk about standard 5-card hand poker. So in this, you're dealt 5 cards randomly from a deck, okay? And then you bet against your opponents that you have the best hand, and if you're correct, then you win the money, right? So that's poker in a really quick, very simplified nutshell. Now, poker hands are ranked from least likely being the best hand to most likely being the worst hand, okay? So in this case, most ordered means the best hand in poker, and least ordered means the worst hand in poker. So bad hands have high disorder and good hands have low disorder. So what's the best hand in 5-card poker? It's the royal flush, okay? A royal flush is when you have the 10, the jack, the queen, the king, and the ace all in the same suit, okay? So for example, a royal flush is shown in this picture here. You have all hearts, and you've got the 10, jack, queen, king, and ace. That's a royal flush. And that's the best hand in poker. So what is the multiplicity of the macrostate royal flush? Okay? So macrostate is the kind of hand that you have, which would be the royal flush. How many ways can you have that hand? That's the number of microstates associated with your macrostate royal flush. Well, here in a standard deck, you've got 4 different suits. You've got hearts, spades, clubs, and diamonds. And so you can have the 10, jack, queen, king, and ace in any one of those 4 suits. So that means that the multiplicity, omega, is equal to 4 for the macrostate royal flush. All right? Now, the next best hand in poker, which is the next macrostate I'm going to discuss, is a straight flush. Okay? A straight flush is when you have 5 cards in a row, all in the same suit, but you don't count the royal flush. The straight flush doesn't count the royal flush. So, for example, as shown here in this little picture, in the one underneath royal flush, a straight flush could be a 3, 4, 5, 6, and 7 of spades. Okay? That's one example of a straight flush. So how many ways could you have that? Well, if you don't count the royal flush, you could have ace 2, 3, 4, 5, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, all the way up to but not including 10, jack, queen, king, and ace, right? So that means that per suit, there are 9 ways to have it, and then there's 4 suits, right? And 9 times 4 is 36. So that means that you have a multiplicity of 36, omega is equal to 36, for the macrostate straight flush, all right? I'll do one more, because it's fun. Let's think about the next best hand in poker, which is 4 of a kind, okay? 4 of a kind. So you have 4 suits, so you have 4 possible ways that you can get, for example, a 10. You've got the 10 of diamonds, the 10 of clubs, the 10 of hearts, and the 10 of spades. So if you have all 4 10s, that's 4 of a kind. Your 5th card, though, could be anything. So what are the number of possible ways that you can get that? Okay, well, if you look at a single suit, it goes ace through king. So there's 13 possible cards that you could have 4 of, okay? But for the 4th card, it could be any other card in the deck. So that means that the multiplicity of the macrostate 4 of a kind would be 13 times 48, which is 624, okay? So that's just a simple example of how you can calculate multiplicities for macrostates and what a macrostate and a microstate are, okay? Hopefully that's pretty clear. So the best hands in poker, as I said, are the ones with the lowest values of a multiplicity omega. These are the least likely hands. Now, what's the most likely hand in poker? Well, if you do the combinatorics, which we'll talk to a little bit later, but for now just bear with me. If you do the combinatorics, there's 2,598,960 possible 5-card poker hands. And about half of them are crap, okay? So having nothing has the highest multiplicity, okay? Because you're going to have roughly, 1.3 million ways to get crap, whereas you only have, 4 ways to get a straight flush. Now, since all hands, when you deal them out, are equally likely, having nothing is the most likely outcome, okay? So that's what I meant when I said that macrostates with larger multiplicities are more likely than macrostates with smaller multiplicities, right? You can think of poker if you need the analogy. Okay, let's talk about entropy, okay? We've talked about the multiplicity omega. The entropy is a measure of the disorder of the system. And the way that you calculate the entropy is S, which is the symbol for entropy most of the time in most text, capital S, is equal to Boltzmann's constant times the natural log of the number of microstates for that system. Okay? So S is equal to K, natural log omega. Now, why would you want to do this? Well, okay, first of all, omega for something like an ideal gas system is going to be a huge number, okay? How do we deal with huge numbers? Well, you can do a couple of things. You can take a natural log, and that makes a huge number manageable, and then you can also multiply it times a tiny little constant like Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. Doing both of those things will make your number for your entropy something that you can deal with on a day-to-day basis. So there you go. Now, the second law of thermodynamics states that the entropy of an isolated system increases in all real processes, okay? And for ideal systems, the entropy can stay the same. The change in entropy going through a process can be 0. But that means that we have an equation here. Delta S will be greater than or equal to 0 for an isolated system undergoing a real process. All right, so in other words, the entropy of a system will increase, okay, if it's undergoing a real process. Another way of saying this is isolated systems evolve in a direction such that the multiplicity increases, or such that the entropy increases. Now, you might have heard of the expression the arrow of time. You might have heard it in a sci-fi show or read about it somewhere. So, the thermodynamic arrow of time is provided by the second law of thermodynamics, which says that in an isolated system, entropy tends to increase with time. So this is one reason that some folks think that you can't go back in time, because that would mean that you're violating the second law of thermodynamics. So that's an idea. Of course, you could dump a lot of entropy in one place to make up for that, but there you go. Okay, microstates, macrostates, and probabilities. The probability of a system moving in time from an ordered macrostate to a disordered macrostate is far greater than the probability of the reverse, right? So if you're going from order to disorder, that's likely. But going from disorder to order is less likely. And that's just because of probabilities. There's more microstates in a disordered macrostate. And so that would mean that you're decreasing your odds if you go the other way. So if we consider a system and its surroundings to include the universe, then the universe is always moving towards a macrostate corresponding to greater disorder. Okay? So sometimes it's said of the thermodynamics, there's all kinds of t-shirts for the second law. The second law of thermodynamics, chaos will reign. Or you might have heard the laws of thermodynamics described as you can't win, you can't break even, and there's no point in trying. So there's some thermodynamics for you. Now, as you can probably guess, knowing how to calculate probabilities and statistics is important for a thorough understanding of thermal physics. We're going to talk about just a few basics here, and then as we go along in our studies, we'll use these basic ideas to do some important work, okay? So first, let's talk about basic probabilities. For independent, equally likely events, like rolling a dice or flipping a coin, you have to add up the total number of possible outcomes. I'll call the total number of possible outcomes big N. You then add up the total number of ways to obtain a desired outcome. I'll call that little n. And then your probability is little n divided by big N. Okay? You might have seen this in a previous math course, but this is just a reminder for you, I hope. Now, let's say that you're dealing with independent events like rolling dice, flipping coins, things like that. Then it's actually pretty easy to figure out the total multiplicity over all microstates. Let's think about flipping a coin. If you flip a coin, usually we say it's either heads or tails. So the total possible outcomes per trial is 2, heads and tails, right? That's it. Now, if you're rolling a cube, a die that's a cube, there's 6 sides. So that would mean that if you have different numbers on each side of the die, 1 through 6, then there's 6 possible outcomes, okay? Now, if you've got multiple trials, say that you're flipping a coin a bunch of times, or you're rolling a die a bunch of times, or you're rolling a bunch of dice, or flipping a bunch of coins, right? That's multiple trials, basically. If you're doing that, then you raise the total number of possible outcomes to the power of the number of trials. So if you're flipping 10 coins, for example, the total number of possible outcomes would be 2 to the 10th power, right? If you're rolling 5 dice, that should be dice, right? Then you would have 6 outcomes to the 5th power, okay? So that's how you figure out the total number of possible outcomes. That would be big N, okay? Now let's say that you've got a standard 6-sided die and there's 6 outcomes, 1 through 6. So the probability of getting any particular number then, let's say rolling a 3, in one roll would be the desired number of outcomes, which is 1, rolling a 3, divided by the total number of possible outcomes, which is 6. So that would be your probability for a single event, 1/6. But let's say that you wanted to know the probability of rolling a specific combination of numbers in order in 6 rolls. How would you do that? Okay. Well, in that case, let's say that you wanted to roll 1, 2, 3, 4, 5, 6. Okay. That would mean that the total number of possible outcomes is the number of outcomes per trial raised to the number of trials which would be 6 to the 6th power. Now, let's say that you want to know what the probability is of rolling 1, 2, 3, 4, 5, 6 in that order. That's very specific. That's one desired outcome, little n equal to 1, divided by the total number of possible outcomes, which is 6 to the 6th power. So the probability of that particular outcome is 1 divided by 6 to the 6th power. Okay, let's look at another kind of scenario for calculating probabilities. Let's say that we have a number of objects and we want to know the possible number of ways in which they can be arranged in a row or in order. So let's say that we've got 4 folks, Bob, Carol, Ted, and Alice, and they're in a line. So how many ways are there to order them in that line from first to fourth? You could list them out. You could go Bob, Carol, Ted, Alice, B, C, T, E, A. Or Bob, Carol, Alice, Ted. Or Bob, Ted, Alice, Carol. You could do that, but it's tedious, okay? So the quickest way to figure out the total number of ways of ordering something is to use the factorial function. So if you have n objects, then there's n factorial unique ways to order those objects. So for our above example of Bob, Carol, Ted, and Alice, there's 4 folks in the line, so that would mean that there's 4 factorial ways to order them, or 24 ways. 4 times 3 times 2 times 1 is 24, okay? Okay, so we use that factorial idea when we're talking about this function, which is called the combinatorial function. And this combinatorial function is very important for calculating multiplicities, which is why I'm coming back to it. Let's say that we're drawing lots for a prize. Let's say there's 3 prizes, they're all the same prize, $5 or whatever, and 100 people have entered to win this, right? So how many different possible combinations are there of winners? Well, the total number of people in the pool is 100, so big N equals to 100 here. The total number of winners is 3, so that's little n here, okay, 3 winners. The total possible number of combinations is given by the combinatorial function, and that's shown here. It's big N factorial over little n factorial over big N minus little n factorial, okay? So for here, for example, it would be 100 factorial divided by 3 factorial divided by 97 factorial. Now, the order isn't important because the prizes are all the same, so we want to control for that. So that's why there's so many factorials, right? That's why there's the 3 choices there. So if we look at our, how many ways are there that folks could win, we got 100 factorial divided by 3 factorial divided by 97 factorial, and that ends up being 161,700. To look at it another way, you've got 100 names that you can draw on draw 1. 99 are left in the pot after you draw 1 out, so that's draw 2, and then 98 on draw 3. But the order isn't important. In other words, the prizes are all the same. So it doesn't matter how they're arranged in the line 1, 2, 3, so you're dividing out by that 3 factorial. Now, this is very different from your probability of winning, which is 3%, assuming that you only put your name in the pool 1 time, right? Okay, I'm going to show you that it's 3% though in just a second. Now, often with this combinatorial function, the language is like big N choose little n, or 100 choose 3 when they talk about the combinatorial function. In other words, out of 100 things, I'm choosing 3. The number of possible ways that can happen is, insert answer from combinatorial function here. So let's figure this out here for our little example of 3 winners out of 100. What's the multiplicity of the microstate you win, assuming that you entered 1 time in a pool of 100? Okay, so what's the multiplicity of you win? Well, that would mean that out of the 3 draws, 1 has already been selected. You. Yay, you. Okay? But the other 2 could be anybody out of the remaining in the pool. So that means that out of the 99 remaining folks, 2 are chosen. So the multiplicity of that would be 99 factorial over 2 factorial over 97 factorial, which is 4,851. So there's 4,851 ways you can win out of the total number of possible outcomes, which, as we already saw, is 161,700. 3 choices out of 100. 100 choose 3. So if you take the multiplicity you win and then divide that by total number of possible outcomes, that gives the probability of you winning, which is 4,851 divided by 161,700, which is 3%, 0.03. Okay? All right. Now, you might be thinking, okay, this is great. She's talking about poker and she's talking about drawing lots, and I'm supposed to be studying thermodynamics, and I just don't understand how any of this could relate. Well, the truth is that we use these combinatorial functions to describe real physical systems, okay? Now, we're going to get to the hard ones. We'll get to the ideal gas. We'll get to the other things, the Einstein solids. But let's start off with something that's a little more straightforward and yet still a relatively physical system that we can talk about, okay? And that's what I'm going to call the two-state paramagnet, okay? Now, a quick review, okay? You should have enough physics to remember this at this point, okay? Remember that if you have an external magnetic field and you have a magnetic dipole, a bar magnet, for example, and you put it in that external magnetic field and allow it to, suspend it in some way. And my analogy here is the compass needle in the external magnetic field of the Earth, okay? Then the magnetic dipole will rotate to align with the external field that it finds itself in. There's a torque, in other words, on the dipole in the presence of that external magnetic field. The torque expression, tau, torque, is equal to mu, the magnetic dipole moment, cross B, the magnetic field, the external magnetic field. Now, once that magnetic dipole is rotated so that it is aligned with the field, its potential energy is at its lowest possible value. The potential energy of a magnetic dipole in an external magnetic field, U, is equal to minus mu dot B, okay? Now, this is for big magnets and big magnetic fields, but it also holds for tiny little magnets, right, in magnetic fields. And it goes all the way down to the atomic level, okay? So let's say that you have a paramagnetic material where each atom has its own little tiny magnetic dipole moment mu. Now, those little magnetic dipole moments will tend to align parallel to an externally applied magnetic field B. And they still have that same associated potential energy function. U is equal to minus mu dot B. But when you shrink it down to the atomic level, quantum mechanics kicks in. Quantum mechanics tells us that individual atoms can have only discrete values of potential energy. It's not a continuous spectrum, in other words. You're not going to have any old energy. It's not going to be at any old angle with respect to the magnetic field. It will only have specific values. Now, in the simplest possible case, and that's the one that we're looking at now, you only have two energy levels that correspond to the magnetic dipole moment being either parallel or anti-parallel with the field, and this is the two-state paramagnet. Now, usually we talk about spin-up and spin-down particles to indicate whether these dipoles are aligned with or against that external magnetic field. Okay, so that's our system. We're looking at these magnetic dipoles for these tiny little atoms, okay, in an external magnetic field. Let's assume that there's N of them, big N, okay? And the choices are either spin up or spin down. Spin up I'll indicate with N with a subscript with an up arrow, and spin down is N with a down arrow, okay? So big N, the total number of particles, is equal to the number up plus the number down. Now, what's the multiplicity of this, okay? Let's say that you have some given number of spin-up particles in a total collection with another given number of particles, okay? So the multiplicity of having that specific number of dipoles being spin up would be the combinatorial function. Big N factorial, the total number of particles factorial, divided by the number of up particles factorial, divided by the number of down particles factorial, okay? And that would be your multiplicity for your two-state paramagnet. All right? So that's how we went from coin flipping all the way to talking about a real multiplicity for a physical system. Okay, hopefully that was a decent introduction to this topic. Don't worry, We're going to talk a lot more about this as this semester continues. I hope you enjoyed it, and as always, I'll see you in class.